Hello everyone. I like strategies. Not as much as RPGs, but they're definitely among the games that I play rather regularly. And one of the strategies that I enjoy is Stellaris. And Stellaris has space. Well, it operates on galactic scale. And it has stars and other stuff. So, and I have a degree in astronomy. So I thought it would be interesting to look at all those stellar objects that they have and give my commentary on it. I will be looking at sort of vanilla game, no mods. I will be looking only at objects that have like real life analogs or were inspired by our current astrophysical knowledge. I will not delve into any sci-fi stuff. I will not talk about. Also, I will not talk about planets, nor about the ships or anything. It will be just mainly focused on star and stellar systems, with a bit side notes on, as you will see further on, galaxies and nebulae. So let's start this note with galaxies actually, because when I went to kind of create the footage for the stars, you need to create a map, and before you create a map, you need to choose the type of map. So I recorded some of the footage on my Steam Deck, and so as you can see right? Yeah. As you can see, there is 10 types of galaxies out there. And yes, and it starts off with elliptical, and that's where just right off the bat the problem arises, because what is the because you can see on the left here what will the map will look like actually, and it's not elliptical. it's it's clearly a disk galaxy that just doesn't have any discernible global substructures, when the actual elliptical galaxies are like ellipsoids. I mean, there are like more intermediate subtypes that maybe have some disk left, but not like this. So this is not elliptical. This is a disk galaxy, and the disk galaxies that do not have any discernible features are called lenticular galaxies. So this is a lenticular galaxy. Okay, so then there go some spiral galaxies, 2, 3, 4, 6. Just skip off 5 for some reason, but okay, why not? All are possible. This is a very, like, I guess what people are classically understand as a galaxy, this disk spiral galaxy. With regards to amount of spirals, well, I think as far as I know, anything goes, and here they present like a very symmetric, smooth, very distinct spirals that go out of the center. In reality, I think we see a lot more shenanigans and different levels of distinction, like different levels of how spirals are distinguished. But I understand that, of course, in context of a game, that would be hard to reproduce the entire galactic zoo. Actually, that reminded me that there is a thing called Galaxy Zoo, and it's one of those like amateur or like civil action thing where you basically there's a lot of images of galaxies, and you can go out there, register, and classify the galaxies on your own, and help do that, basically help comb through the endless amounts of data. So yeah, just as FYI. But overall, I have no qualms with representation of spiral galaxies. These 4 spiral galaxies. And then there is a ring galaxy. It's here, I suppose it's presented like a subtype or a variation on elliptical, quote unquote, which is basically, again, a galaxy with no discernible substructures. Well, in this case, except the ring, so it's like a disk, but the star density falls off towards the end here, which kind of creates this ring. Well, why not? Ring galaxies are also a thing. I don't know how they're formed or anything. There might be it might be a result of some galactic interaction, but I don't know. But I do know that the ring galaxies exist. Then there is a barred spiral. It looks very here it's not even idealized, but hyperbolic barred spiral, with only 2 spirals, and as you can see, I mean, you can see the kind of there is an idea behind the structuring of this, and so on the top is classic galaxies, and on the bottom is a variations of them. Though I would say that barred galaxies is somewhat also quite prevalent, quite normal. They're not a special subtype. And of course, in reality, barred galaxies have multiple spirals. For example, the closest example is Milky Way, but it's a bit more murky with Milky Way because it's hard to observe it. It's hard to understand the global structure of our galaxy while being in it. It's like trying to map a city whilst looking out of the window of your apartment that is on the 3rd floor. So it's kind of hard. But we do know that our galaxy, I think, has a bar, and last works, I mean, there's no consensus on how many spirals we have, but it's from 3 to 5 maybe. So yeah, bar does not mean that there's only 2 spirals. There most likely will be 2 spirals out of the ends of the bar, but they can also go out of other parts of the central region as well. Then go the weird ones, kind of. And there is a starburst galaxy. So here it is a galaxy that has 3 spiral arms, but all on the same side. In astronomy, what we call starburst galaxy is a galaxy that has an elevated over average star formation rate. So basically, where we observe more young bright stars than usual. Usually that's a galaxy that usually there's galaxies that are in the process of a merger or have recently experienced some collision or something. Something happened, because to elevate the star formation rate, you need an influx of matter. You need to concentrate a lot of matter, clump it together, and it will provoke this rapid star formation when it's all together and gravitationally unstable and starts fragmenting and collapsing, whatever. you need something to happen for that. It's not something that something normally occurs. So usually it's accompanied, or it comes as a consequence of a merger, of a collision, of a flyby of another galaxy that would disrupt the matter distribution. It is not anyhow connected to 3 spiral arms being on the same side, but I will not say that this this galaxy shape is not impossible, though it definitely doesn't look very like stable. It probably, if something like this exists, is probably like also a result of some collision or merger or whatever. But I wouldn't say that it's not possible. Then there is a cartwheel. So it's kind of a variant of 4-arm galaxy, but with spirals coming out of not of the center, but there is like a ring before that. And also the spirals are not very discernible. Also, I think, wait, is there actually 3 spirals on the... Yeah, on the picture there is actually 3 spirals instead of 4. Like here's drawn with 4, and on the left it's 3, I think, if my eyes don't lie. Interesting. So we don't really have cartwheel type of galaxy. We have a cartwheel galaxy, which is a name for a very specific galaxy that's also weird, and I will have an image a bit later on. But it's like also was formed as most likely as some kind of from some kind of collision or merger. With regards to this structure in particular, I wouldn't say that it's impossible as well, because again, fuzzier, less discernible spirals can exist. That's something that's okay and observed. So I wouldn't see any problem with that, though I don't think that this is somewhat defined as a separate class of galaxy shape. Well, and lastly, there's spoked. Oh god, sorry, I was too quick with all that. This is obviously unrealistic structure because it just looks like a cut up. Obviously, nothing is in the galaxy world that looks like this. Is this too smooth, too symmetric, too geometric? Galaxies are messy. So yeah, this is just pure fantasy. And also a funny thing, it's kind of, again, from the structure, it appears that this would be a variation on the 6-arm spiral. But on the picture here, on the icon, it has 8 arms. And here on the left, it has 7 arms. 7, like, sectors. Interesting. I don't know. But it's kind of, I think what's, again, as it's a game, I would look at it more on a, like, gameplay side. And I think that this shape is sort of a perfect one for, like, arena type multiplayer matches where everyone is like spawns on the ends of these sectors, and then there's like 7 players, and you just race to expand to the middle, and then start clashing here, basically giving like some time to develop alone without any interaction, and so on and so forth. The same with the bard spiral. I think is like kind of divides the battlefield into 2 not really interacting parts, kind of 2 isolated regions that can develop on their own. But this is like just gameplay wise. Okay, so this is about the galaxies. Let me show a slide related to it. Yeah, this is like what I I've written down some little summary. So elliptical is not elliptic or ellipsoid. In the game, in reality, it is. Starburst is a different thing. Cartwheel is possible, but isn't called that way, and Spoked isn't real. And this is a cartwheel galaxy. That is a real image, I think, of JWST. Yeah, so it has this, I mean, it kind of looks like a cartwheel, but this is definitely like something happened here, and also this whirls, and so interesting. Yeah, but this is just a name for one specific galaxy and nothing else. Okay, now on to star. So, and we'll start with single objects. So there is 11 objects, stellar objects. So there's 11 variations of stellar objects that are there. Overall, there's nothing else. And they can also come as a part of a binary or a trinary, and we'll talk about that later. So there is 6 main sequence stars. So this Roman 5 denotes, in spectral classification, denotes a star on the main sequence. There is one giant, this I denoted by Roman 3, brown dwarf, which is a failed star, a wannabe star, and 3 stellar remnants, a black hole, neutron star, and a pulsar. Technically, neutron star and pulsar, the same type of thing, but we'll discuss it later. And for that, I will start now the footage for stars. Let me just put it into position. So what we'll do is I'll read the descriptions for them, and I'll discuss I'll tell my thoughts on it. So we'll start from earlier type stars to later type stars. It's just how it's earlier and later is just a naming convention. It's not really has to do anything with age that much, though kinda is, but never mind. So earlier type stars are the ones that are bigger, more massive. So it's OBA. Later type stars are FJKM. So we'll start with earlier types, the structure that I had on the slide. So B star. The large class B main sequence stars are very bright and blue. Although somewhat rare, the luminosity of these stars make them among the most visible to the naked eye. So very short description, quite reasonable. So they are indeed very bright. They are blue, though in the game they're represented somewhat as violet. And my comment to this is that we wouldn't see stars as violet. I don't think. I mean, it is true that this star emits more in violet and shorter wavelengths than in blue and longer wavelengths. But I suppose that how stars are represented on screen in game is supposed to represent how we would see them with a human eye. And human eye, well, it has its own sensitivities and kinks of light perception. And the thing is, so I won't go into this because I'm not an expert, but as far as I know, we perceive violet, we're less sensitive to violet than to blue, and since it still emits a lot in blue, we would see this thing as blue and not violet. Like, to see something, I think to see something violet, it needs to be like specifically only emitting in violet. If it emits in everything else, we just wouldn't see this as violet. So that would look more bluish than violet. and they do note that in the description. They say it's blue, but then in the game it's violet. I don't know why. Somewhat rare, that's true. They are rare, and there is a general rule that the more massive the object is, the rarer rate of it, the smaller rate of its occurrence. It's roughly, the distribution is roughly a power law with an exponent of -2, if it says anything to you. So yeah, if you're more massive, you're more rare. That's true. And they are indeed quite visible on the night sky. So if it's close, so I mean, we can see those stars with the naked eye further out because they're so bright. Okay, then goes the A star. I will also talk about what's going on the surface, but at the very end. So A star, there's relatively young white or bluish white main sequence stars are typically among the most visible to the naked eye. They are large and rotate very quickly, but will eventually evolve into slower and cooler red giants. So, okay, there's a bit more to unpack. First is relatively young. What I assume they mean by that is that, again, there is a general trend that stars of higher mass live less, simply because you need to kind of resist a bigger gravitational pull, and for that you need you resist it with basically gas pressure, and so you need, for higher mass you need bigger pressure, and to get that bigger pressure you need to be hotter, and to be hotter you burn hydrogen stronger and quicker, and so therefore you run out of it faster. So I'm sorry if you can hear those breaths. It's tough to speak. Anyway, so yes, indeed, since it's among earlier types, heavier stars, it doesn't live as long as later type stars, but I have to note that A stars are not that different in mass from later type stars, because so the mass range that A stars occupy is somewhat a bit less than 2 solar masses, and just slightly more than 2 solar masses. So it's like a fraction of so it's a range of a fraction of a solar mass around close to 2 solar masses. And the lowest mass A stars can live up to 1.5 billion years. It is still less, of course, than all lower mass stars, but well, they say relatively, I guess. You see, when you say relatively, I guess you get a pass for everything. But I just what I find weird is that they note this on the A star and not on the B star, because for the B stars, the mass range is significantly larger. So it starts again at a bit more than 2 solar masses and ends somewhere around 16, like 16, 15 solar masses. And and they and even the lowest mass B stars live only for 200 million years. So that would be more relatable to B stars than to A stars, and I don't know why they specifically chose to write that for A stars. And given that there's some A stars or lower mass A stars live for as long as 1.5 billion years, they can easily be a situation where you have an A star that is older than later type stars, like a G star or whatever. So I don't know, but okay, relatively. White or bluish white, yeah, very blue here, but okay, they can. I mean, it's like a general trend here that I noticed, that they write one color in the description, but they depict it with a bit of a like colder color. Like, so they write blue for B, and they do it violet. They write white or bluish white for A star, and they make it light blue, or like quite discernibly blue. And also, I think they you'll notice it for the next stars as well. Then they say they are large and rotate very quickly. So they are large. Also, again, the general trend: the more massive the star is, the bigger it is in radius. Why did they not write it for the B star? I don't know. And regarding large for A star, again, A stars are not that different from mass than from one solar. Like, I mean, it's just around 2 solar masses. Compared to 1 solar mass, which is our sun, it's not. I mean, it's a factor of 2. In astronomy, that's nothing. It's a very small difference. Considered to be, because we operate in like orders of magnitude. So it, especially when there are stars up to 100 plus solar masses, this difference of 2 is not that much. And in radius as well, this is a difference of 2. So like A stars have 2 solar radiuses in radius. That it does transform into like difference of 8 in volume. So like A star would fit 8 suns, but which is kind of an order of magnitude, 8, close to order of magnitude. But I don't know, it just doesn't seem that much of a difference to me astronomically, and it would fit much more with the theme of B stars than A stars. But okay, relatively large, yes, if you compare it to like later star types. Okay, rotate very quickly. Also, I guess this is with general trend that the higher your mass, the faster you rotate. That's also been reported, observed, measured. They do rotate quicker than the lower mass stars, yes. And will eventually evolve into slower and cooler red giants. True. This is true. This is true. Then goes F star. So F-type stars are fairly large and often referred to as yellow-white dwarfs. Although they often emit significant amounts of UV radiation, their wide habitable zones have a good chance of supporting life-bearing worlds. So again, fairly large. F-type stars are like, again, have inhabit a rather narrow mass range for like from slightly more than one solar mass to like 1.5, 1.6 solar masses, and the radius relation to radius in solar radii is about the same. So like 1.5 solar radii radius, not that much. So they are larger than the sun, true, but I don't know. This is like very vague terms describing size. I'm just, I guess, picnicking them. But I'm using this as an opportunity to tell something about the stars. So don't judge me for nitpicking these descriptions. Yellow white, completely white here. Although they often emit significant amounts of UV, again, the question what's significant, I don't know. They do emit more in UV than lower mass stars, but okay, I guess you can say that. Their wide habitable zones have a good chance of supporting life-bearing worlds. Maybe that I don't. I'm not really well versed in astrobiology, and it was not really. It's not a part of a curriculum, really. It's like a very young field that is that rarely where has a full separate dedicated program, like a course. So I don't know anything about that. I mean, in the simplest way, I guess you could talk about habitable zones just like in terms of temperature range, because like you need temperatures, because I think typically what is called a habitable zone is basically where the water can be liquid, and it corresponds to a certain range of temperatures, and for a star you can just easily estimate the range of this, where these temperatures will be, just assuming that, well, just assuming that it emits as a black body, and just, you know, and then fades away as distance squared. And yeah, you can make estimates of what the temperature would be at every distance. And based on that, yeah, F stars would have a bit further out zones, and I guess that would make them wider, maybe. But yeah, astrobiology, I won't touch. Don't have much to say about this. G star, okay. This is the one that was like most is written about, I think, out of the stars. Often referred to as yellow dwarfs. Isn't it yellow? Gold yellow or peace yellow. G-type stars actually range in color from white to slightly yellow. Main sequence stars fuse hydrogen for roughly 10 billion years before they expand and become red giants. So this is true. They fuse hydrogen into helium, and for the masses around which ones G stars have, which is around 1 solar mass, and yes, by the way, Sun is a G-type star. It happens. It can there's enough hydrogen to sustain such fusion for 10 billion years, and then they become red giants. Although their lifespans are shorter than K-type stars, Worlds inside the habitable zone of a G star often enjoy optimal conditions for the development of life. Well, that we know because we live around a G-type star. So we kind of, the only instance of life we know, well, this star has a support for that. The only note here is about the lifespans, and I'm not sure why they pressed it, because 10 billion years is not that far from the age of the universe, as much as we know it, which is like around, well, close to 14 billion years. So, like, why is that important? Like, I think this 10 billion year lifespan is more than enough, especially since we have evidence that the life developed to what it is in 4.5. So why do you need longer lifespan than that? I don't know. And why that would be an advantage. And a question is like, well, why would it be an advantage if you can't use like most of that time? Because the universe has a shorter life. The universe lived for a shorter time than that. And like, yeah, and I feel like the edge of the universe is a bit of a harder bottleneck here than the lifespan of the star itself. So yeah. I had a thought, but I lost it. Anyway. So yeah. That's true. Although, yeah, maybe I had a thought that maybe in Stellaris universe, the universe has lived for longer, so that's why it's important. But I don't know. Oh, yes, another thought. And the thing is that even if you consider, the thing is, so that because not only the universe has lived like only for 14 billion years, which is shorter than the lifespan of stars starting with K-type, the stars have not formed right away. Like, when the universe banged, the stars did not start to form like on the first second. No. The first stars are theoretically assumed to appear after 150 million years, which is not a lot in the billion time scale, but still. But the thing is that the first stars should have been different, because in current models of stellar formation, when you contract the cloud to the size of the star, to get it to the size of the star, you need to have effective cooling mechanisms, because otherwise the gas would heat up too quickly and get to equilibrium without getting to the size of the star and to the conditions that would support hydrogen fusion and so on and so forth. So you need to cool it off while you're contracting to get to what we see. And the main cooling component, or the main way this gas cools, is through dust that isn't there. But the dust is formed in stars, in the late stage stars that have expanded low temperature envelopes, and they kind of and carbon starts to concentrate there and condense into dust. So if it's formed in the stars, there should have been no dust at the time of the first stars, And it kind of creates the questions, and kind of creates the question: how did they cool themselves to form? So, whatever way the stars, I mean, they must have formed somehow. Otherwise, we wouldn't have dust as well. But this mechanism should have been different, and the mass distribution should have been different, and like everything must be different. Unfortunately, we cannot really look at them, because like we can look into the past this far, but we can't resolve anything there. Like some galaxy at best, maybe. Well, not resolve, like just as a blob. To see some galaxy as a blob, as a dot, maybe. But not more than that. We cannot study stars that deep into the past. And you'd also think that, well, they live for so long. If they live for so long, well, longer than the universe has lived, we should see these stars in our galaxy. And this is like what is called a hypothesized population 3, the first stars, because the lower mass first stars should still be alive because they can live for so long. And yet, we do not find them. We do not see any evidence of their existence in our galaxy anywhere. We have two populations of like younger stars and older stars. And older stars, they're going up to like 10 billion. The oldest stars we see are about 10 billion years. Nothing older than that. Not really. Well, maybe a bit. I mean, there might be like vague age estimates that would like indicate 11 or 12 billion years, but not the first stars, not the very first population. We do not find it anywhere in our galaxy. So even in that sense, we can't. I mean, the higher mass, of course, died long ago. The lower mass should still exist, but we don't see them anywhere. And this is like one of the mysteries of astrophysics. Is like, where are the first stars? They should still be here. Maybe that means that the first stars, there were no low mass first stars, and all of them just already. We don't know. Or even the low mass stars died quickly. We don't know. I think we don't know. And I'm not in that field, so I'm like a bit of a speculating here based on what was said on lectures at my uni. But I think we don't know. Okay, so next star, K star. Okay, these main sequence stars, sometimes referred to as orange dwarfs, that does look like Fanta, are a fairly common sight. The same comment about distribution of star masses. They're stable on the main sequence for up to 30 billion years, roughly true, yes, meaning that worlds orbiting a K-type star have a longer than average window to evolve life. Again, the same comment, they push at this evolving life stuff. I wouldn't say so. I wouldn't say that it has significantly, like, it technically, yes, but not that they had time to use that privilege. They didn't. At least in our universe. In Stellaris universe, I don't know. Maybe the Stellaris universe has lived for longer. I have not found any evidence for that. I don't. Do they have a codex or something about? I don't know. Should have checked, but whatever. Then M star. The most common stars in the universe, often referred to as red dwarfs. Indeed, red. The low luminosity means they're difficult to observe with the naked eye from afar. True. Although they typically have an extremely long lifespan, Red dwarfs emit almost no UV light, resulting in unfavorable conditions for the most forms of life. So most common stars, true. Again, the same power law applies here. There's more of them than of any other main sequence star. Um, about UV light, it's a more. They do indeed emit not much of that, but I don't know how favorable or unfavorable that is for life. Maybe it was important for Earth on earlier stages when the Earth didn't have ozone layer yet. Maybe it kind of helped with some chemical processes. I don't know, so I won't comment on that. Overall, looks very reasonable description. M, red giant. With a large radius and comparatively low surface temperature, red giants are stars of moderate mass in a late stage of stellar evolution. Their expanded stellar atmospheres and high luminosity make for distant habitable zone orbits. So, So, large radius, true. Comparatively low surface temperature, true. Otherwise, they wouldn't be red. Stars of moderate mass. I don't know what they mean by moderate mass here. Because, so infrared giants are. So, almost all stars, except for very massive ones and for very low mass ones, they all go through a red giant stage. So by very low, I mean starting below 0.5. Why? Because when these stars run out of hydrogen and start to contract, they simply cannot heat up for this through this collapse enough to start fusing helium. They might light up some layer sources, like basically that if the star, and I don't remember when the stars start being fully convective, but I think if you're like around 0.5, a bit less than 0.5, you're still not fully convective. That meaning that you have like a helium core, and you have some still hydrogen in the upper layers, and that the upper layer hydrogen can start after contraction burning, but this does not help much, and if anything it just strips off the upper layers, and either way they do not get to helium burning, which means they turn into white dwarfs right away, and they're called helium white dwarfs because they are composed mostly of helium. So that's why they don't go through the red giant stage. An interesting note here is that, so as you might have guessed, that since these low mass stars, and like actually this 0.5 mass is like where the M stars start. So M 0.5 solar masses and below, this is M type stars. So they live very long, longer than the universe has lived, and that would mean, as you might have guessed, that we cannot possibly just encounter helium white dwarfs alone, like in single systems, because all M dwarfs that has lived, they couldn't end their lives. They're just born and they live and have a very long time to live yet. So they can't. We possibly couldn't see a helium white dwarf. But the fun fact is that we do. We do see helium white dwarfs, and especially very low mass white dwarfs. Like 0.07. I think the lowest mass of a white dwarf found was like 0.07 solar masses. So we do find them, but we find them in binaries or multiple systems. And that's because in closed binaries, stellar evolution can go very different. And you know, this is very interesting. So even though these stars on their own could not end their life so quick, and we, I think, do not see solitary helium dwarfs unless they were somehow thrown out of the system. Then we would see a solitary helium dwarf. We do see them in binaries, which is cool, I think. Very interesting. Very interesting. Yeah. But then beyond 0.5, they all go through the red giant and form. And if their mass below 8-10 solar masses, they form CO, or like carbon oxygen white dwarfs, because this is what they mainly consist of. And if they're larger than 8-10, they still, the lower masses, like just a bit more than 10, they still go through the red giant phase, but they form a neutron star. And then if you go further out, things can start get more unstable there, and these stars during the late stages can just like lose their surface layers, just expulge them through some violent processes. And so that typically, if they wouldn't do that, they would also have this huge low temperature envelope that would identify it as a red giant, but they throw it away through whatever process goes on there, and leave naked, hotter underlying layers, and that kind of identifies it as not red giant. So they kind of don't go through that if they're very high mass. Yeah. So I don't know about moderate mass, because it can like, because there's like a huge variety of masses that go through red giant stage. Their expanded stellar atmospheres and high luminosity make for distant habitable zone orbits. With habitable zone, I don't know, because this is a late stage of the star, so it had some system for a while. And I suppose that inner, like, stars that were planets that were close to the star might, well, they're probably gone. The outer, like more distant from the star planets, probably would be unaffected by this process. And technically, yes, the habitable zone would shift, because yes, the luminosity during this process rises, but like, I wouldn't talk about any prospects of forming life there, because like, it's like not actually. Well, I don't know how long this stage takes for the lowest stars, but it's not that long comparatively to the main sequence. So I don't know if there is even enough time to form any life there, especially when it was barren and cold for so long. I don't know, like, but I guess in the context of ruling a stellar empire that needs to colonize worlds, you wouldn't really care about that. You wouldn't really care about if there's life prior to you. You would just be like, you could still terraform it and just enjoy the conditions. Just spend less on like supporting the needed conditions, because like you check the luminosity box. I guess that's what they imply here. Okay. So close. And now we get to brown dwarfs first. So brown dwarfs are substellar objects that lack the mass to sustain hydrogen fusion. True. Roughly the size of large gas giants. True. They have a much greater density. Makes sense, since they are more massive than large gas giants, but their size, that gives them high density. The low luminosity and comparatively small heat generation means that the planet orbiting them are unlikely to support life. Makes sense. They are indeed very low luminosity, and they just live off whatever energy they got from gravitational collapse. Well, plus deuterium burning, but I think that's not for very long. Maybe, I don't remember. But even then, it's not like the main source of energy, because it's like because there's very little deuterium compared to hydrogen, so it cannot be sustained for long because it's just much less of that. So yeah, so it's kind of true. The weird thing about this is that for some reason brown dwarfs in this game occur only in binaries or trinaries, never alone. I don't know why. I mean, maybe because historically, because of their low luminosity, it's kind of hard to find them on their own. So there were people searched for them in the systems, like, and basically used all the same methods you need to find a planet, like basically to find anything that is massive but cannot be seen. And that is possible only in like a system with some luminous component, and by looking at how the properties or positions or whatever of luminous component change, you can infer what is going on there. And I think the first brown dwarfs were found that way, but we have found solitary brown dwarfs. They can exist for sure. They can exist for sure. I don't know why they needed to put them necessarily only into a system, which is also weird, because if you look in the game files, they have like a class for systems consisting of only brown dwarf, but it's never used. I mean, I haven't checked in a way that, load 100 maps and do statistics. No, I haven't done that. But this is what the Stellaris wiki says, that brown dwarfs are always in the binaries. Okay. A choice, I guess. So no. Neutron star. Okay, these incredibly dense stellar remnants are sometimes created when a massive star suffers a rapid collapse and explodes in a supernova. True. Although their diameter is typically as little as 10 kilometers, true, they're very small, their mass is many times greater than an average G-type star. Wrong. Well, I mean, many times greater? No. So, what we know on neutron stars is that so the lowest masses of neutron stars that were found are around one solar mass, which is the average G-type star mass, kind of. And the biggest are like a bit more than 2. Theoretical limit on how big neutron star can be is around 2 to 3 solar masses. So it's like in a range of from G star to A star typical masses. So a factor of 2 plus max, that is not many times greater. They're not that massive. And they cannot be that massive because otherwise they would just collapse into black hole. So this is not true, at least in our universe. The gravitational waves and radiation emitted by neutron stars must be carefully navigated around, slowing the sublight speed of ships. Now that's also a bit dubious because, so first radiation. So these things are insanely hot. That is true. They are like, when they're born, I think they're like 10 billion Kelvin. Insane. When they cool down, it's like 10 million or 1 million Kelvin, which is still insane. So they emit mostly thermally, they emit mostly in X-ray, like in very short wavelengths. Since they're so small, the luminosity is not that great, like around 1 solar luminosity. So they're not that luminous, and that's why it's hard to find them alone as well. But they do emit insanely harsh radiation, and that might be possibly damaging to ships. True. But gravitational waves, what are you on about? So gravitational waves are formed or are created when you have some periodic change in the space-time curvature. Well, if we are talking in terms of theory of relativity. And typically the most powerful and noticeable ones are created in binaries. So like black hole binaries or neutron star binaries. This is the ones that we have been able to detect with LIGO. But this works because so there is 2 stars that are, well, neutron stars are not that massive, but I think the what compensates here is how close they can get. So we have 2 massive objects that very quickly rotate around each other, and that naturally creates this changing periodic pattern in the space-time curvature, and this is what creates gravitational waves. But when you have a solitary star, what kind of gravitational waves will you create? I mean, technically you can, if you have some kind of inhomogeneous density distribution inside an object. That would create a somewhat inhomogeneous space-time curvature, inhomogeneous gravitational field, that if you rotate the object, will also, like this deviation will also rotate and kind of create a wave. Oh, because there is like a delay, because the gravitational interaction also goes with the speed of light. But this gravitational wave would be insanely weak, and I don't think that neutron stars are very homogeneous. They're so squished. They must be like the most homogeneous thing in the universe, probably. So I don't see how a single neutron star would create significant gravitational waves that you would need to be carefully navigating around. Two neutron stars, maybe, yes, if they're very close and they rotate very quickly, they can create sort of like this detectable gravitational waves. But alone, no. I don't think so. I don't think so. Yeah. So pulsars. So pulsars are highly magnetized neutron stars that emit beams of electromagnetic radiation. As the star rotates, the radiation beam is only visible when it is pointing directly at the observer. This results in a very precise interval of pulses, which sometimes is so exact that it can be used to measure the passage of time with extreme accuracy. The radiation emitted by pulsars interferes with deflector technology, rendering ship and station shields inoperable. So, I think that this is somewhat a weird choice, because whether the neutron star is a pulsar or not is very observer dependent, as you can see from this description, because you can identify something as a pulsar only if its beam is directed at you sometimes. Well, and also it needs to have, for this to work, it also needs to have a misalignment between the rotation axis and the magnetic poles, or magnetic axis, I guess, because the beams are concentrated along, because these are concentrated along the magnetic poles, and if they would be aligned, then the beam wouldn't move. But if it's not, then it moves, and very precisely, and that's how we see it all. So, in the context of a galactic scale, so you look at it like from the upside, and you also have like empires that span stars. I don't see how, like, I don't see why you would denote specific stars as, I mean, I guess you could expand this definition into all neutron stars that just not only directed at you, but just in general are capable of doing that have enough magnetic field to create these beams of radio. Well, essentially, if I remember correctly, I have not refreshed my memory on this. But the thing is that, so there's a lot of electrons around that thing, and there's a powerful magnetic field, and the electrons are kind of accelerated inside that field, and that causes them to emit, which is called the Bremsstrahlung, if I haven't butchered that pronunciation, which is like yeah, I don't think it's called anyhow else in English. They just borrowed this German term. Yeah, and this is how this radiation is created. So it kind of needs this high magnetic field, and these electrons are also kind of moving along these lines and like whatever, and that's why it's created along the direction of poles and so on and so forth. So I guess you could expand in this like observer less case. You could expand it to just neutron stars that have enough of a magnetic field to do this, to create these beams, and they have a misalignment of a rotation axis and a beam that would like make it so that for even one system they would appear as a pulsar. That's possible. But to be honest, what I don't know and I haven't found information about is that whether all neutron stars are capable of being pulsars. Well, I haven't searched that hard, truly. But I understand that some of the older pulsars that have slowed down might have a weaker field that is not capable of producing like strong beams, or maybe not capable of producing beams at all, kind of. But they still have a magnetic field. They still all have quite significant magnetic fields, although again there is a huge range in them, and there are arguably neutron stars that have weaker magnetic fields. I haven't looked up what's the threshold for creating such beams, so I wouldn't. So I would say that there is still. I feel like there might be pulsars that, especially older ones that rotate much slower, that they don't have as a strong magnetic field, and they might not be able to operate pulsars as pulsars to anyone. But at the same time, I think we have observed neutron stars that are capable of being pulsars, but they're just not oriented towards us with their beam. So, like, I feel like in this area there's a lot of ambiguity and, well, a lot of research to be done. But yeah, I don't know. So I just found weird that they kind of separated pulsars into a separate class. But I guess if you see it as just stars, neutron stars that have quite strong magnetic field, but at the same time not very strong, because if it's very strong then it becomes a magnetar, and that's a very different thing and has a bunch of their own funny effects, because this magnetic field is just somewhat tearing the star apart, and it creates all sorts of stuff. And I don't know if they function as pulsars, but interesting stuff. Yes. So, but there is a cool bit of trivia about them here, that it is indeed can be used as a very precise time measurement devices. The radiation emitted interferes with deflector technology. Oh, I don't know what is a deflector technology here, and why would it render it inoperable. Technically, they're not brighter than usual neutron stars. They just have magnetic fields, and that causes all that stuff. So, yeah. Okay. Black holes. So typically formed as a result of the collapse of a very massive star at the end of its life cycle. True. Black holes have extremely strong gravity fields that prevent anything, including light, from escaping once the event horizon has been crossed. The gravitational waves emitted by black holes interfere with FTL drives, making it harder for ships to escape from combat. Extremely strong gravity fields? No, honey. This is a common misconception, I think, of black holes by people who don't know astronomy. They don't have special gravity fields, I'm sorry. A one solar mass black hole will have a gravity field of any object with one solar mass. I don't know if the one solar mass black holes, but like a 10 solar masses black hole, it will have the same gravitational field as any other 10 solar mass object. There's no difference at all, completely. It is exactly the same. What is different is that all this mass is inside its event horizon. That's the difference. And to other non-black hole objects that have the same mass, you can't just get that close as you can to a black hole. But if you would get, technically, if you would get into a 10 solar mass star, if you would get inside of it, you would stop experiencing the layers of mass that you have passed. So the gravity pull would actually decrease as you go inside, as you go deeper inside. So it kind of will behave differently compared to the black hole in that case. But outside, it's exactly the same. Even like a centimeter outside 10 solar mass star, the field will be exactly the same as at the same distance for the black hole. So don't tell anything about extremely strong gravity. No, they don't. You just can get much closer to them than you would for like a star. Okay? Because everything is inside event horizon. Event horizon is quite a small object. Not object, but like quite small in radius. But it is true that if you pass an event horizon is kind of defined as the radius at which you need speed of light to sustain like circular orbit. Like you need a speed of light to be able to orbiting this object without falling in. So yes, so once you're inside, you can't do anything. You're trapped, and light will not escape it as well. Again, the gravitational waves, black holes are especially not inhomogeneous in their distribution of mass. So a lone black hole would not create any gravitational wave whatsoever. No, just no. 2 black holes, yes, very much, amazingly so. 1, no, forget it, never, not a single, never, no, not at all. What I do want to comment here though is this grayish stuff around it. What the hell is it? Wait, where is the larger? No. Okay, I don't have a... well, maybe I do, but... oh, yes. So, what the hell is this grayish thing? I suppose it's supposed to be an accretion disk, but for some reason it's dark and is just lighted by this white arc around the black hole. What? And just like it's literally just illuminated by that, and it's just reflecting this light. So there's just some kind of clouds going around that are lit up. No, this is not how it looks. No, this is not how it looks. If you want to see how it looks, I can refer you to the 2 only images of black holes, where the accretion disk was colored according to its brightness temperature. So it's like orangish red, and the entirety of it emits. It's not like something at the very border here that's very bright and shines up on everything else. No, it's the whole disk is warm and emits. Of course, it's kind of, I think, brighter closer up, because it's like it starts to rotate quicker and there's more friction, so it's more energetic, and it's more dense, so there's more friction, and so there's like more energy being turned into thermal and then re-emitted. So I would expect a gradient of brightness towards the black hole. True, but the whole thing emits. The whole thing is the whole thing emits, yes. And it does not look like that. Also, the question is, where the hell does it get this disk? Because this is very small, and because it's so close to the black hole, the speeds are so high, the energy output, the energy emission, and it loses like energy that way. So it's like, so what happens? Like, so this gas whirls around, experiences friction, redistributes rotation energy into thermal energy that is then re-emitted. So it loses energy, and it causes it to fall into the black hole. So this is why it's called accretion disk, because it accretes onto the black hole. And since it's so close and the rotation is so fast, it eats up the accretion disk rather quickly. So if you have a black hole, maybe when it's born, you would get an accretion disk from the matter that is left from the star that produced it, because like it can turn into a black hole a bit earlier than everything falls into, and the stuff that is not perpendicular to the rotation axis, of course, will fall in quickly. No disk formed. The things that are in the plane will rotate for some time, I suppose, and would form this disk, I think. But that would be eaten up pretty quickly. But that would be eaten up rather quickly, I think. And to get such an accretion disk, you'd need some donors. And here it is a solitary black hole. It doesn't have any star to feed on. So it would not have an accretion disk. It would be just dark. You can't really find black holes without accretion disks. So in signal objects. I mean, you can through microlensing, but beyond that, no, you can't. Those two images of black holes, they were like images of super massive black holes in the centers of the galaxies. Those are very dense environments, and everything whirls around them. So once in a while, they gobble up some star and destroy it by tidal disruption. So they have an influx of matter always to keep this accretion disk. Single intermediate mass black holes? No, how would they? Unless, again, they are in the system. Then yes. Then the other star might get gobbled up. When it kind of starts to expand and starts to fill in its so-called Roche lobe. Basically, this is like an area of space where the matter gravitationally still belongs to the object. So they expand and fill up their Roche lobe. Everything outside of the Roche lobe starts siphoning out to the other object. And that would happen, and that would create this accretion disk for the black hole. But alone? No. So what is this? I don't know. It's just some dust. It's like some I don't know, it looks like some clouds, some dust clouds just whirling around with some central lightning here, produced by I don't know what. Yeah, that's my take on this black hole. But again, I might be wrong. Okay, so I think that's it for the... So I think that's it for the single objects. We've gone through all 11 of them. Now we're going to get to binaries. And binaries here are... There's only 10 possible... Oh, by the way, these icons that I use, I think they're icons from the game. Like when you have... This is like what is called sprites, I think. It's like on a map, when you're like looking at a galaxy in this map mode. This is which sprites are used to display stars of these types. But I took them from Stellaris Wiki, the images themselves. But technically, I think they're from the game files. The same here. So binaries. There are only 10 types of binaries that you can encounter in this game. And they have like very specific combinations of star types. And I'm going to comment on whether or not they're possible. So, A-type star from plus pulsar, I think possible, because like all you need for that is a star that is more massive than a star. Well, not just that, it must be quite a massive star. Like it must be either high mass B star, so like beyond 10 solar masses, or an O star, and that is possible. This combination is definitely possible. And then this component would evolve faster. And yes, so when you have a binary, you always kind of assume that they were born together and they have the same age. It's pretty much the default assumption. I don't think that there is like... I think the events in which you kind of like get a companion from somewhere else is rather rare. Like mostly I think they're born together. B star plus a neutron star, the same thing. You just need a more massive star. M giant plus B star. That's also possible because again, B stars also go through the giant phase, and you just need a more massive B star than this one, and it would evolve faster and get a combo of M star plus B star. Because like and B stars are rather like have a rather wide mass range, so this could be like a lower end of masses for B stars, and this is like higher. Possible. M giant plus F, also possible, very much. B plus B, no questions, possible. M plus J, yes, why not? They live rather long. All of them live rather long. Same with K plus F and J plus F. Seems possible. A plus F also. There's no problem with them coexisting on the main sequence together. Possible. A plus T, also no problem. T's are like brown dwarfs. Yeah, brown dwarfs are denoted T here. They're forever. They're existing forever. They don't evolve that much. No problem with that. Also, another thing, so the binaries here can be two types. They can be a closed binaries when they're like all in the center and they're surrounded by a circumbinary disk, or they can be separated and each of them can have their own disk. This is also possible. There's nothing wrong with that, though the only note here is that closed binaries that have their own circumbinary disk, they're often interacting ones, and the evolution proceeds a bit differently to like more separated stars. And this is not reflected here in how they're not interacting anyhow. They're just chilling out there in the center. But I understand why. Because, you know, it's would be insane to implement all of that, and this is not like the goal of the game. It's just cute decorations and very pretty ones. Oh yeah, oh god, I forgot. I remember what I forgot. We wanted to look at the surfaces. I wanted to comment on the surfaces of stars as well. Let me do it quickly because it's a very short note, because they're sort of all very similar. They all look the same, and all stars kind of look the same. The only thing that changes, oh yeah, this is a very good site. They all look the same. They all have these same moving patterns. No, please don't close. They have the same moving random patterns going around, a bit of clouds going on. They all look the same. They just are of different color and different size. And that's it. How realistic that is? Not really. I mean, we definitely know how the stellar surface looks only for Sun. For the others, we can't possibly resolve that. They're too far. We can only maybe, for the closest, brightest star, we can somewhat resolve some global kinks, but not this close. So we know only how the Sun looks. And what we typically see the very common occurrences like spots and granulation, they're not presented here. And the Sun has what's going on the Sun is like a crazy bunch of dynamical effects. And as I was told in solar astrophysics, they have so much data now, the theory cannot keep up, because it's insane how much stuff is going on there, and all this data is collected for that, but explaining it all is just insane magnetohydrodynamics and other effects and physics of plasma, and people are drowning in work down there. It's not like this. It's not these weird wiggly shapes that are randomly moving around. If you want to look, there are a lot of images of the Sun online, how it looks up close, how it looks in different lines, and so on and so forth. It's not really like that. But I do not judge them for not making an accurate representation of the star of the Sun's surface. I mean, it's fine. It looks pretty, and it looks like a star. So I think that's enough for the game. It's just not a harsh criticism or anything. I mean, nothing here is criticism, by the way. It's more of a I saw it. I saw what they say. I'll look at what they say. I look how they present it all. I just comment on it. My thoughts. Yeah. So I'm not judging harshly whatever their how they depict the stars here, because largely we don't know. We know how the sun looks, and actually, like, modeling this level of detail would be insane. So I'm not like mad that they didn't do that or anything. It's of course fine how they did it. Like, just random squiggly lines going around, some stuff going on. It's fine. It's fine. It's fine. Not very accurate. Not how the sun looks. But it's okay. The choice to make all stars look the same up close is a choice. Which I also don't judge very harshly, which is like, it's like, okay, again, it's not really the goal of the game. It's not really like its main attraction. So it's fine that they reused the textures and effects and just recolored them. That's fine. But I would want to note here that earlier type stars should look different on the surface than later type stars, because so in stars there are two main ways of energy transfer: convection and radiation. And in earlier type stars, they have convective energy transfer in the core and radiative in the upper layers. The later type stars have vice versa: radiative in the core, convective in the outer layers. So convective is like a more mechanical way when you have like so there is a distribution of temperature. It's hotter closer to the center, colder closer to the surface, and you have like colder gas on the top and hotter gas on the bottom. And the hotter gas, when it gets heated up, starts to rise and kind of overtakes over the cold one, and cold one like drops down. And there's like this whole whirling process, like just like in your cooking pot with water, the same thing happens there. And that's why the sun has this convective process in the upper layers, and that's why the surface is so dynamic. And these granules are visible, because these granules are basically this like blotches of matter that are circulating. It's like convective bubbles, basically, kinda. It's also connected to the magnetic field, but whatever. I think, and so, but in earlier type stars, they have a radiative energy transfer, which is not dynamic at all. It's just photons that transfer the energy. So you would expect the earlier type star surfaces to be very inert, very smooth, very calm. I think that's at least the expectation. Like, not many spots or anything. It's just very, very like chill. So they could have implemented something like that. It's not that hard just to make like a more chill animation, more chill effect, more smooth and homogeneous surface. But they didn't. It's fine. It's fine. It's fine. Besides, we don't really know how it looks anyway, so whatever. Yes, so back to binaries. Sorry, I forgot. Yes, so all binaries are fine. And what else? And yes, and they're closed binaries, they're separated binaries. Closed binaries should interact, but I understand that it would be hard to implement. And of course there are much more variations of like star masses in binaries and what is going on there, like, is just insane. There is insane variability, insane diversity of what goes on in the binaries. It's yeah, it's nowhere possible to represent it all, so they just at least try to do some diversity. 10 is fine. 10 is fine. Could be more. There could be much more combinations, but it is what it is. It happened. They did what they did. It's fine. Another thing that I remember that I want to say is that, like, you might have noticed that I told you the mass ranges for the stellar types. And you might have noticed that starting from A and down to M, the mass ranges are very narrow, like fractions of solar mass. Like there's a fraction, like for A, there's a bit of a fraction of solar mass. For G, so for F, for G, like it's just a bit around some 1 point something. Like the same for K, it's also just a bit less than 1 solar mass, and then up to 0.5, and then anything from 0.5 down to 0.08, where the brown dwarfs start. This is M. So very, very narrow ranges. Whilst for B, it goes from 2 something down to 16. And then O is everything upwards from 16. Why is it so, like, inhomogeneous? Why these ranges are varying so much in mass? And the thing is that this is a spectral classification. So it is based on the features and like shapes of spectra of stars. And they just happened so to be connected also to masses. Because, physics. And this classification was mainly done in optical because, well, this is what we have had longest access to. Like for the very long time, optical is the only thing that we could see, really. Because first, the atmosphere, like, it's very transparent in optical, but in UV, no. And further out is just not letting anything through. The same in the infrared, there's a lot of water that absorbs stuff and other chemical molecules that absorb stuff there. So it's just like a fog. Like it's like in infrared, just a huge fog covering our planet. Plus the planet itself emits in the infrared, so it's like so a ground-based infrared telescope would be like looking from on top of a huge flashlight. You don't want that. So most of the spectrum was kind of close to us until we went into space. Until we went into space. And that's why all these classifications rely on optical. And it just so happens that these classes of stars are mainly have discernible kinks in the optical, and like this FJ, AF, JK, they mainly have features. They mainly meet somewhere around optical, and they have features, a lot of different features in the optical that make them easy to differentiate between. But B and O, they are mainly emitting in the shorter wavelengths in optical, and their features in the optical are not that different to each other over a huge mass span. So that's the reason. Maybe they have more discernible features, and maybe like they can be like a separate classification based on this X-ray spectra, or not X-ray, UV and X-ray spectra. But I don't know. Like, are they even works in that regard? Maybe, but I mean, they're probably observing them in that wavelength regime, since they are the brightest stars in that. But I haven't seen the works, and I haven't heard anything about differentiating between different star masses in UV for the high mass stars. But maybe they do that. But maybe that is a real thing. Maybe not. I don't know. But historically, this comes from spectral classification. Yeah, and that was focused on the optical part, and the classes that are like more mass shorter, like they're sliced in mass by shorter ranges, are just the ones that have more discernible features in the optical. They have more variation in the optical, and therefore the features very distinctly change, and you can like more easily make up different classes there. So yeah, that's a little side note, just a little interesting fact for you to enjoy. Yeah, so binaries. Yeah. Okay. And then they also have trinaries, which they have only 4 types, and they went rather conservative here. So basically, this is trio of the latest types, of earlier types, then middle types, and then also for some reason B and K and dwarf. But this is also possible, I think, because even like it's kind of pushing here on to controversial territory, but the lowest mass B can live up to a few 100 million years, and I think that's enough for K to leave to get onto main sequence. I think that's enough. So I guess that's possible as well. Yeah. And of course, in IRL, there is much more variability in the trinaries and much more combinations. I mean, even more than in the binaries, obviously. And I suppose in multiple stars, insane things happen. Yeah. So, and before I move to the last slide, I also want to give a short note on the nebulae. Let me set it up. So the nebulae. So the nebulae is not very diverse here. They all look the same, like this gray bluish blotch of matter. They don't have descriptions for them except for the gameplay effect, which is blocking sensors. And an interesting effect here is that when you go into the system inside the nebulae, you have these sort of gassy filaments that are lighted up exactly corresponding to the light of the star. So it means that this matter is somewhat quite reflective of the the stellar emission. And so I would say that, yeah, this is a very funny one, very funny coloring. But so what I would say about this, so IRL, we have a huge diversity of nebulae and like just interstellar medium objects. What I suppose these are supposed to represent is like molecular clouds, probably giant molecular clouds where the stars are born. I'm not sure. It's like very vague. It's very like indiscernible, but it seems like mostly made out of gas. But yeah, I can't really attribute it to something very particular among the all nebulas that there are, because they're like supernova remnants, there are planetary nebulae, there are like dark nebulae which are mostly out of dust. There are these molecular clouds. There are like also there are reflective nebulae, and there's a bunch of other stuff, a bit like if you want to go into detail and subtypes and so on and so forth, depending on the circumstances and the stars that are there and so on and so forth. So this is not all is not represented here at all. They just have this one type of weird bluish gas blotches, which is, I guess, fine, but not really representative of anything that we see out there. Except maybe the closest is molecular clouds. This is my best guess. And then when you go into system, you see this kind of reflective behavior of them, which, well, when you have a reflection in space, it's usually the dust that does it, because the gas cannot reflect, really. At least not in the... Well, yeah, the gas cannot really reflect. The gas only can re-emit in lines. So that... and that would like change the spectrum of the... That would like change the emission, whilst the dust can kind of preserve the same spectrum somewhat when they reflect. So I would guess that it's... Well, I would not assume that they wanted it to be out of gas here, because what I really wanted to comment here is that you would not see this inside the system. Even if you're inside the nebulae, even inside a very dense nebulae, like molecular cloud, it's still very diluted. It's still very diluted, and the systems are rather small. So I wouldn't say that... I mean, it can be checked by very simple estimates. I did not do this, but I'm betting that you will not be able to see any nebulae inside your system if you're inside the nebulae. It's like the fog, essentially. Like when you're in the fog, you can see your surroundings easily. It doesn't seem like any fog is around you. But when you look outward, you get more and more stuff on the line of sight, and you get this... You start to see the fog. And the less dense the fog, the further out you can see, right? Before it starts completely obscured. The same thing is applied, exactly same thing is here, but it's much more diluted. And even though the scale is much bigger, in case of a system, it's still not that big of a scale. And I would bet that you would not see any nebulae stuff inside your system. You would just not be able to see that. You would just see through. You would probably see nebulae like maybe at its like a few parsecs away from your system, you would start seeing, like, it would start appearing as if like something is obscured, that you're obscured, like a few parsecs into it, but not within the system. So that's not realistic. You would not see any filaments or whatever in your system if you're inside the nebula. No, sorry. That is not real. But I understand it's a cool effect. It looks very cool. And you kind of still need to... And it's also like kind of gameplay-ish in a way that you kind of still can understand that you're within the nebulae inside this. When you're inside the system, you can still, from this information, understand that you're inside the system, and that might be gameplayingly an important information. So I understand the choice to still make it visible, but that's not realistic. Okay, I think that's it on video materials. And I'll proceed to the last slide, which is what I did not see. For some, it is not represented here for some reason. So first of all is O stars. I don't know why. This is puzzling to me. Why did they start from B stars? Why don't they have O stars? White dwarfs. So we see neutron stars, but no white dwarfs. That's weird. Also, fun fact: I've wrote it like a fantasy race here, though in science literature it is common to write it like with an F instead of VE. But I come from a fantasy background, so I wrote it that way. Also, I don't know why there are no white dwarfs. I have no idea. Even though they have, I mean, maybe they assume that their galaxy is not that evolved. That the only only stars that could have turned into neutron stars have evolved. Actually, well, I mean, if you assume that this galaxy had like only one event of star formation, and we're like several millions years into it. No, not me. No, the life wouldn't evolve. You would need a few billion years for that. Yeah, so I suppose that. But no. Would that? Well, yeah. A stars. Yeah. No. You would still have white dwarfs. Sorry. Yeah, I just thought that if you assume that this galaxy had a single star formation event, that like basically the galaxy is born, all stars are born at the same time, then if you would assume that to evolve life to like this level of intelligence, you would need also this 4.5 billion years. You wouldn't have any O stars, but you wouldn't have any B stars as well. So that doesn't work. And A stars also live less than that, so you would have white dwarfs from A stars and from B stars as well. So that doesn't add up. Sorry. Unless the life evolves faster in that universe, in this, like in Stellaris, and it's able to evolve in a few million years, and then you would have you're like 100 million years in, then all stars all are dead, but not enough for white dwarfs to appear. So you have only neutron stars and black holes, and still have B stars. Like the the galaxy has existed just for enough of time for all neutrons, for all stars to be gone and turn into black holes and neutron stars, but for none of white dwarfs to yet appear, I guess. That would also explain why there is no pre-main sequence stars, because although I think in the lowest mass pre-main sequence stars they can exist. They can go through this stage for like several, like maybe about 100, can push up to 100 million years, I think, but I'm not sure. Like, we have this conservative estimate of 30 million years, but this is like for one solar mass. For lower mass, it's longer. I don't know. Yeah. So I'm not sure how this is sound, but yeah, but I also miss the young stars. There's like zero representation for them. Everyone is just at least main sequence for some reason. I don't know why. I guess such systems would not be considered viable for, but black holes are not viable for colonization anyway. But black holes are cool, I guess, and young stars are not that cool. I guess maybe they did not include them because they would be like just decorations, and quite complicated because you would need to add like gas disks around them, and there would not be any planets there to be like colonized, so it would just like, I don't know, maybe because of that. Then for some reason other types of giants don't exist when we observe them. I mean, they might not live as long as red giants, because the red giants are like the last stages, and this and the line and the other stages of giants, the other luminosities, no, not other temperatures. The giants' other temperatures are kind of like a very quickly passed stages. I think like they go through them during the expansion. So like expand and they cool off, and then you go through all this rainbow essentially during this process. And this is a relatively quick period, but then you stop at the red giant. I think I might be wrong here, but we still catch them in these on these stages. And they certainly would keep existing on the time scale of the. And even I say quick on the life scale, on the time scales of star lifetimes, which is still more than the time scale of the game, which is about 1,000 years. So, interesting. So they could still implement them, and they would still like nothing would happen with them. Then interaction in closed binaries. Okay, I mean, I have mentioned that basically in closed binary there should be interaction between the stars that would lead to a bit of a different evolution. But I understand that it's hard to implement. Then more multiplicity in systems. Basically, we see star systems that have much more stars than 3, and all type of shenanigans and variability and diversity all is there. Could be implemented, but I understand that they didn't want to bother with this, and 3 is enough, I suppose. But it could be. But this is what's happened. I'm just noting common things in our universe that are absent. And time variability. So on the one hand, the time scale of the game, which is 1,000 years long, is not that much in the cosmic scale of things, right? So the galaxy wouldn't change that much. The galaxy would indeed look like stable and unchanging, and certainly stars would not certainly experience much of rotation, and like no major stellar evolution would happen. However, we know that there is still time variability on the timescales lower than 1,000 years, especially, for example, in young stars. Oh, I know that because I know that closely because I'm in that field. But we have, what kind of variability we don't have? But most importantly, we have these eruption events. There are Efuori type outbursts that last for 100 years. So and it's a huge change in luminosity, a huge one, and it happens quite rare, but it happens for 100 years. So it could happen in a game on this timescale. Then there are XORs, which have X-loopy type outburst, which has lower amplitude, but it has a timescale of a year, and it repeats several times over decades, and so on and so forth. And this is also obviously can be noticeable on the timescales of the game, right? So there is on this timescale variability to find. Also, supernovas. Well, if you consider this theory that all O stars died, you wouldn't have supernovas anymore. But it is estimated that there should be around one supernova around each 4 to 500 years, and the last supernovas that have been observed in our galaxy were the ones observed by Kepler and Tycho Brahe around 400 to 500 years ago. So we're kind of statistically bound to have one soon. And this is also something that could happen in the galaxy of the game. Something could, one supernova could blow up easily or even two, over the length of the game. So there is much time variability yet in space that exists on the timescales comparable with that of the game. And it could be displayed, but I understand that it would kind of come. But they have events, so they could make it like an event type of thing. Though I understand that it would be kind of hard to model, I guess. Or maybe not hard to model, but a certain amount of effort needs to be put into this. And I suppose that on the traditionally astronomical side of things, they don't want to bother that much, as I feel, which is understandable. The game is not about that. The game is more sci-fi-ish. They're more interested in doing astral rifts, wormholes type of stuff. Understandable. But this is what is missed anyway. So, yeah. So that's it. That's all what I had. Thank you for listening. Hope you enjoyed it. And have a nice day. Or sleep. Or whatever time you're watching it in. Bye.